The title of the paper chosen by our group is A Discrete Event Simulation Model of the Viennese Subway System for Decision Support and Strategic Planning. In this paper, a discrete event simulation model of the Viennese subway network has been developed. As shown in the schematic plan, the Viennese subway network has 5 lines U1, U2, U3, U4 and U6 and consists of 90 physical stations, 10 of which are crossing stations where 2 lines meet as over here, and in one single case over here 3 lines meet. The 3 renowned stations have been marked. For example, this marks Stephansplatz, this marks Praterstern, and this over here marks Westbahnhof. Headway optimization, that is, the average interval between trains on a subway station, needs to be optimized so as to meet the passenger satisfaction. The optimization should be done keeping in mind the population growth, increased carbon emissions, tourism and economic factors, that is capital and operational expenditure. So, the main aim of this paper is to improve present-day systems performance by headway alterations and determine consequences in terms of number of vehicles, mileage and passenger satisfaction. Further, this paper presents a way to find number of additional passengers that can be accommodated under the current headway setting. Passengers generally prefer tight headways, which will reduce their waiting time and thereby a lower passenger travel time, which would tend to lower the system utilization. This utilization needs to be optimized. To achieve these objectives, a simulation model has been developed. The simulation model was implemented in AnyLogic, which is a tool supporting agent-based, discrete event and system dynamics simulation methodologies. Further, JGraphT has been used, which is a graph drawing open source software component available for the Java, C#, and JavaScript languages. Next, I now introduce the simulation model and concepts related to it as stated in the paper. First is the subway network model. The figure over here shows the basic structure of the subway network model. Here, 2 subway lines, one grey and one white are present. Both these have logical stations L0 to L9. Every logical station is assigned to a physical location Pj. If 2 or more logical stations share the same physical location, as over here, P2 shares the same location with L2 and L7, grey dotted arrows allow passengers to travel from one line to another. Now next is the diagram depicting the passenger and vehicle interaction. Here, all logical stations are divided into an upstream and a downstream direction, and both the directions have their own queue for waiting passengers, whose capacity depends on their respective surface area. The alighting passengers, that is the passengers descending from a train, do not spend much time on the platform, since they either leave the station or transform to another line, and thus they do not interfere with the waiting queue. Next section of modeling is the passenger modeling. Passenger generation is driven by a time-dependent Poisson process that starts at 4:50 am and continues until 1 am. This graph over here depicts the number of passengers within the Viennese subway system over operating hours on an ordinary day when no mass events were scheduled. Here, the time frame is divided into intervals of 1 hour, for which a respective origin-destination matrix provides the hourly passenger rates. For each passenger, a designated passenger path consisting of logical stations is constructed. For example, for a passenger traveling from P0 to P8, the path constructed is L0, L2, L7 and L9. Construction plans were used to measure the distance from the middle of one long platform to the middle of another line's platform at a subway station to estimate the transfer time of passengers from one line to another taking the passenger's mean walking speed as 1.34 meters per second. Next, the last section of modeling is the vehicle modeling. The Viennese subway network operates with two different types of vehicles. The vehicle type used on lines U1 to U4 has a passenger capacity of 878 passengers, while the vehicle type employed only on line U6 has a capacity of 776. Vehicles always begin and end their tour at either one of the end of line stations. They are released in accordance with the respective line's current headway, which potentially changes hourly in order to meet the time dependent demand, that is the hourly passenger volume. The minimum interval between two trains on a station is 1.5 minutes. Thus, a vehicle is not allowed to leave a station before 90 seconds have elapsed since the departure of the preceding vehicle. If it is lower than 1.5 minutes, bunching phenomena occur. Some of the terminologies used in vehicle modeling are the vehicle interstation travel time, which is equal to the time difference between a vehicle's arrival at one station and its arrival at the following station. Dwelling time, which is equal to the time difference between a vehicle's arrival at a station and its departure. And the boarding and alighting time, which is equal to the time difference between a still standing vehicle opening its doors and closing them again. A statistical analysis of vehicle data revealed that vehicle interstation travel times are not time dependent but direction dependent. The graphs over here depict the frequencies of observed travel times on the various subway lines. Most interstation travel times are like the graph shown over here of Paterson to Vorgartenstrasse. Generally, crossing stations close to the city center have a longer vehicle travel time away from them than towards them. This is caused by longer dwelling times, which is depicted clearly in these four graphs over here. Thus, Stephansplatz and Westbahnhof both share this phenomenon. Since the majority of vehicle interstation travel times appear to be almost normally distributed with a longer tail on the right side, the log normal distribution has been used here. Now coming to the vehicle-based key performance indicators selected for validation, which are vehicle cycle time, that is the vehicle travel time from one end of line station to another, and the accumulated vehicle occupancy ratio at crossing stations for validation. Here in this table, it can be seen that the mean of the cycle time here is a bit higher than the target values, than the respective target values over here. But it was approved of by the Viennese transportation providers experts. Accumulated vehicle occupancy ratio is based on counting data gathered from the vehicle's doors via infrared sensors. This data is shown over here. It expresses how big the share of a line's daily accumulated passengers on board a vehicle at a certain station is. These resulting values are compared with counting data, and this approach is used to adjust the passenger routing.
For addressing the Viennese public transportation system provide a strategic goal, two scenarios were devised. The scenarios being the headway scenario and the passenger scenario. In the headway scenario, the headway basically is the time between arrival of two vehicles is varied, and in the passenger scenario, the headway is not modified, but in place of that, there is an increase in the number of passengers. So now let's look at the original headways. So the headways of the Viennese subway system from Monday to Thursday, there are different lines and for different timings. Say for line U3 and timing 7 to 7:59 a.m., the headway was 3. This means that every 3 minutes a vehicle will arrive, and the additional loads are 19% of the passengers to at least one transfer, out of which 16.5% do one transfer and 2.5% do two transfers. The rejected passengers, these are the passengers who for some reason do not complete the journey from the source to destination, so they are excluded from statistics. All other passengers are taken into consideration, and the mean and maximum transfer time are 2.31 and 7.1 minutes respectively. So the headway scenario. So what exactly is a headway? So headway can be considered to be the inter-arrival time between two consecutive vehicles. So in the headway scenario, what happens is the headway is manipulated. How is this manipulated? So basically, there are factors from 0.5 to 2 the step size of 0.05. So basically 0.5, 0.55, 0.6 to 2. So basically 31 different steps. So each is multiplied with the headway we have seen in the previous slide. And then the headways which we get are the manipulated ones and they are used further. So now let's consider a step size of 0.15 for displaying on the screen. So as you can see in this figure, the headway factor is 0.5, 0.65 other factors. We'll discuss about 0.5 and 2. So when it's 0.5, what does this mean? That every half the duration a vehicle is arriving. So the total mileage, that is the total number of kilometers that the vehicle will be, all the vehicles will travel during the day is this. Whereas if the headway is 2, so this means that the double the time a single vehicle will arrive. So basically half the kilometers of the total kilometers the vehicle will travel a day. So you can see if the factor is 0.5, the number of the mileage is this, and when the headway factor is 2, the mileage is this. Now the rejected passengers might be because of there are surplus number of passengers on the station. So if it's 0.5, that is very quickly the vehicles are arriving, so there are no rejected passengers, whereas for 2.0 there are 11,138 rejected passengers. Now active vehicles, the mean of the active vehicles are basically the number of vehicles that are running. So if it's 0.5, then more vehicles will be running because every short duration a vehicle is departing. So 170, and if it's 2, then there are 39. We have to take into consideration how many vehicles are available. As far as I suppose, there are 123 vehicles that are available. Now travel time. So the travel time is the total time for traveling. So 0.5, for 0.5 the travel time is 9.2, whereas for 2 it is 12.9, the total time including the waiting time and the in travel time, everything included, the transfer time and all. So what we can say is because of the waiting, this time is increasing. Now in vehicle time, the time spent inside the vehicle when the vehicle is moving. So if it's 0.5, it is 7.56, and if it's 2, it's 7.05, 7.04. Reason being, the vehicle drives a little bit faster when the headway factor is 2.0 in order to compensate for the delay and also for the jitter because of the other vehicles. There are too many vehicles running on the line, so might be that is the reason why this in vehicle time increases, because one vehicle has to wait for another. Then waiting time, the mean waiting time for 0.5 obviously will be less because quickly the vehicles are coming, so it's 1.2, and for 2.0 it is 5.41. So waiting time also increases with the headway factor. Now the transfer time. What is the transfer time? Transfer time is the time elapsed from transferring from one line to another, say from U1 to U2. That is the transfer time. So basically the transfer time, the time for changing the line is almost the same for both. It's not affected. Reason being there are two number of customers, number of passengers per square meter. So there is ample of space on the station. Then there is vehicle utilization. Vehicle utilization implies the number of the number of passengers who are currently traveling versus upon the capacity. So we can see that if it's 0.5, the vehicle utilization is 6.81, whereas for 2 it is 28.63. So with increase of headway factor, the vehicle utilization also increases. Okay, now let's look at whatever we have discussed graphically. So the total vehicle mileage with the increase of the headway factor, this is the mileage is decreasing, and the number of maximum vehicles, active vehicles, so with increase of the headway factor, this is also decreasing. The headway scenario again. The vehicle utilization, this is the mean and this is the maximum. So with increase in the headway factor, the vehicle utilization is also increasing, we can say linearly, and the number of rejected passengers with after 1.3 the number of rejected passengers is increasing. This might be because of the delay, because of the waiting time. What we can say is the travel time increases with the increase of headway factor, reason being the waiting time is increasing. Then the transfer time is almost the same, and the in-vehicle time initially as 0 0.5, it decreases a bit and then it is a constant. And with respect to the passenger times ratio, this is the headway factor and this is the share of the total travel time. So with respect to travel time, the in-vehicle time is decreasing, the wait time is increasing, and the transfer time remains a constant. So that was the headway scenario. Now we are heading towards the passenger scenario. So what happens in the passenger scenario? The headway stays the same. The passenger generation is increased. How is it increased? The factors of 1 to 3 in a step size of 0.05. So there are 41 total steps are multiplied with the number of passengers, and that's how it's increased. The goal over here is to determine the bottleneck and boundaries. So basically, how much the network can handle with the current settings, how many passengers the network can currently handle with the current settings is what we get over here. Now there are two cases over here. The station capacity is restricted, that is limited, and in the second case, the station capacity is not restricted, that is we consider it to be unlimited, which is unrealistic. But just for consideration, what happens if we increase the station capacity? We are considering this case. So, okay, this is the result of passenger scenario, limited station capacity. So passenger factors, we are considering in a step of 0.15. So from 1 to 2.95, we are taking into consideration. So when it's 1, so basically the number of passenger less. So rejected passengers is 0, whereas when it's 2.95, you can see the rejected passengers per day is way too high. Then the travel time is less when the passenger factor is 1, and the travel time is drastic 11.74 when the mean travel time, when the passenger factor is 2.95. Why is this? This is because of the waiting time, because there are so many passengers. So at every station there has to be many passengers alighting and many passengers are boarding, because of which there is a lot of waiting time of the vehicle. Then the in-vehicle time is almost the same. We can see it is actually decreasing. Why is it? Because at the end the waiting time will increase, and in order to make sure that the travel time is in bounds, the speed is a little bit high of the vehicle. Then the waiting time, we can see that with the increase in passenger factor, the waiting time is increasing over here. The transfer time is almost the same between two stations when we are changing a line. Then the station utilization, we can see with the increase in passenger factor, yes, the station utilization is also increasing, and the vehicle utilization also increases with the increase in passenger factors. Now let's take a look at its graph. So okay, we are here. The vehicle utilization mean and max. So with the increase in passenger factor, what we can say is that the mean vehicle utilization and the max vehicle utilization is increasing, but we can see that beyond 1.8, this over here is a straight line, but over here it's becoming a curve, so it is no more linear. Then the number of rejected passengers from 1.3 onwards, it is increasing. What we can see over here is with increase in the passenger factor, the transfer and in-vehicle time, the in-vehicle time and the transfer time and the in-vehicle time is almost a constant, but there is an increase in the travel time due to an increase in the wait time. And passenger time ratio, if we compare with the total share of travel time, so the in-vehicle time is decreasing with respect to it, and the wait time is increasing with respect to it. The transfer time is almost a constant. So passenger for unlimited station capacity, the passenger scenario. So over here there are no rejected passengers. Instead of rejected passengers, they are abandoned passengers. So what are abandoned passengers? Abandoned passengers are the passengers who remain in the system and do not get picked up due to overcrowded vehicles. They are basically standing at the station and they are waiting for the next vehicle to come. So the for unlimited station capacity, let's look at the results. So for factors from 1.2.95, we can see that at 1 there are abandoned passengers 27, and the abandoned passengers are increasing as the passenger factor is increasing. The travel time, this is also increasing, the mean travel time. This is again because of the wait time, and you can see this is a way too big a number. Reason being, there are abandoned passengers who might be missing 2, 3, or 4 vehicles, due to which their mean travel time inclusive of the waiting time is way too high. Now the in-vehicle time, it is almost the same, nothing to worry about. And the waiting time, so basically the waiting time, as I said, is increasing with the increase in the passenger factor. The transfer time always is a constant. Over here also it's a constant only almost. Then the station utilization, because it's an unlimited station capacity, we can see that as the passengers are being accumulated at the station, they are going on missing the trains. So by the end, when it's 2.95 passenger factor, the station utilization is way too high. The maximum is above 100, reasoning it's unlimited. So with respect to the previous one, then the vehicle utilization is also increasing down the line. Let's look at it graph. So these are the graphs. The passenger factor, the travel time, as we can see, is increasing due to the increase in the wait time. The transfer time and the in-vehicle time both are a constant again. And if we compare it with the travel time, then we can see that at 2.15 to 2.2, what's happening is the in-vehicle time is lesser than the waiting time. That is, the waiting time is exceeding the in-vehicle time. So basically, the passengers are traveling less and waiting more, which is not desirable. And the transfer time is kind of dropping, almost a constant, but kind of dropping. So what inferences can we draw? The headway scenario revealed that factor lower than 0.55 leads to bunching of vehicles and increase in the passenger travel time. What is the meaning of bunching of vehicles? That there are too many vehicles, due to which the travel time is increasing. Then the factor of 1.80 requires at least 154 vehicles and 123 are available. This will, if this is possible, then there will be a decrease in travel time of 30 seconds. If the factor is 1, that is the current scenario, 122 vehicles will be needed, and currently it's working fine. If a factor is greater than 1.30, this leads to overcrowding of the stations. Factor is equal to 1.20, then the increase in the passenger travel time is by 30 seconds. These boundaries give some idea for determining a feasible solution. Now, for passenger scenario, what does it reveal? For the limited version, it reveals that for factors greater than equal to 1.3, about 2.2 million passengers, leads to overcrowding of stations. Here, they can use both a passenger factor as well as a headway factor to tackle the situation. The unlimited version reveals that for factors greater than equal to 2.35, leads to many abandoned passengers, which is undesirable. We've seen that in the graph. And for factor greater than 1.75, it leads to the increase in travel time due to waiting. The mean vehicle utilization also increases in the unlimited version. The U4 and U6 suffers from overcrowded stations first as compared to the others. So situation can be handled and tackled. Currently, the real world system, that is the factor is equal to 1 works fine. It needs no modification, but planning is required for future perspectives. The simulation and graph that are presented in this presentation will help in the planning. The references are so far and so on. Thank you.